Hello, welcome to another video on waves for the AS Physics course, and this one's on diffraction, something we haven't done in lessons yet. Luckily it's an easy equation, something easy to apply, but it's a bit of a strange idea, and I thought I'd make a video about it. Hopefully it will help. Now, we've talked already about diffraction, which is the effect that when you get wave fronts coming in like so into a barrier, you can have a barrier like this, for example, then there is somehow an effect with the waves where not only it just continues forward, but there's also this kind of bending sideways, which is here it's exaggerated, but you get this kind of bending effect around objects with waves, whilst particles don't do that, right? If you throw a particle like this, then it either goes there or bounces here and bounces back, but it doesn't sort of turn around corners like that. Now, when you have a gap for the waves to go through, we saw that the waves do something like this, and they spread out like that, right? But what I hadn't discussed with you very much, or not at all, was that when that happens through a small enough hole, you get this effect here. Okay, so say this is your gap and that's your wavelength, the distance between two wavefronts as always. What happens is that as it goes through a single slit, a single hole, effectively every point here along the gap acts like a point source of waves. So you end up getting waves going in that direction, waves going straight here, and waves going like that, as if they were individual sources. So what happens is that they interfere. Even though it's one wave coming in on one slit, it interferes with itself in a way, because some of them are bent sideways, and therefore they change in their slightly in their phase, and so they have a phase difference now with respect to this one that continues straight. And the same thing happens with these. So as you know already from what we've talked about, if the phase difference is a multiple of 2 pi, n times 2 pi, then that is constructive interference, right? Constructive interference. And if the phase difference is an odd multiple of pi, right, then these are half wavelengths, so then you get destructive interference. Here I'm talking about pi's and 2 pi's because this is phase difference, right? So here we're talking about the difference in the angle, so the difference in the place of the wave. So some waves will be here, and the next wave is interfering is here. Depending on how they add, you can have a constructive or destructive interference, right? So if it's 2 pi difference, then you were saying that this wave meets the other wave when they're exactly one wavelength apart. So these two waves meet. If you continue this one, hopefully you can see that they're meeting. Even though they're shifted by a whole 2 pi, they meet the constructive interference because they both up, both down at the same time, and the crests and the troughs accordingly. When it's pi, it's only half a wavelength out of shift, so out of phase, so then you get a destructive interference. And here you need to make sure that these are odd numbers of pi's, right? So n pi's, you can think about it as n pi, where n is 1, 3, 5, 7, etc., right? Because when it's 2 pi, 4 pi, then this is going to be constructive, right? And here for this one, n would have been 0, 1, 2, so any number, because we're multiplying it already by 2 pi. Right, that's for the phase difference. The path difference, it's the same thing, but with lambda, right? One full lambda for constructive interference, and lambda over 2. Now we can say n plus a half, for example, times lambda. Okay, this would be when n is 1, this would be 1.5. When n is 2, this would be 2.5. When n is 3, this is 3.5. So always half lambda out of phase. So this would be for destructive interference, and that would be for constructive. Okay, this is all just, I'm going through it quickly because we've already gone through all of this a bunch of times. So what happens? Well, there's going to be an angle here and an angle there at which you're going to get a destructive interference. The first destructive, the center is going to be a maximum because the phase difference is 0 and the path difference is 0, so that's going to be a maximum. And on the sides you're going to get your first minimums. So there's an equation that can help us calculate what angle this is going to be, theta. We're going to look at that equation in a sec. And so therefore in a question, if they give us the width of the gap and they tell us the distance to the screen, and we can find out theta if we know the wavelength of the light. So that's good. We can predict at what angle we're going to get the minima. So what do we mean by the angle? Well, from here, the center to there, right? This angle, kind of, that one, going into the screen. That would be our first destructive, and then that would be our second maxima. That would be a different angle, right? And here in the center you get a maximum. So you get maximum, minimum, maximum. And this circular pattern, hopefully you can see that in 3D it looks like a circle, not just a screen where you get bright spots and dark spots and bright spots and dark spots like that in a screen. But if you look at it in 3D and the light's going in through a hole, you're going to get that circular pattern. Should make sense, hopefully. So what's the equation that we need to know? Well, first of all, let's use some words that they give us here. So one of the words that we need to know to use is the central. So this is the central maximum as it's here. Okay, so that's the central maximum. We need to know that term, which is pretty standard. Then there's a subsidiary maximum, which is the next ring along. So this would be the subsidiary maximum as it says there, right? And in between there is a minimum. So there's a central maximum, then there's a minimum, and then there are subsidiary maximum. Okay, hopefully that's intuitive enough. Just a few words. So the theta we were talking about, which is this angle between here and the first minimum, is a measure of the diffraction, how much the diffraction there is, right? If this theta is very big, it means that there's a lot of diffraction, and if that theta is very small, it means there's less diffraction. So I will, it's linked to the spreading out of these circles, right? Okay. And just to show you on the other diagram, this one here, you see that's the theta, right? So this is in 2D, and that's what it would look like in 3D. But in 2D, this is easier to understand. That's your wavelength, obviously, and that's the width of the gap B, and this is the angle. So the bigger this angle, the more diffraction, so the more spreading out there is. That makes sense. So if we want to make sure that this is odd numbers only, you can either say n lambda with 1, 3, 5, 7 for n, or you can just use the same n as here, and 0, 1, 2, 3, but you say 2n plus 1, where if n is 0, you get 0 plus 1, you get 1 pi, which is the first destructive. If n is 1, you get 2 plus 1, which is 3, you get 3 pi. If n is 2, you get 4 plus 1, which is 5 pi, so then you get your odd numbers. You can do it with this, using the same counter as this one here, or you can use it with this one and specify that this n is a different n to that one, so it's not just a counter, it's only odd numbers. So this would be a more general way of talking about the condition for destructive interference in terms of the phase difference. Okay, anyway, back to the thing where we were before. If we want to describe the amount of diffraction, we measure the angle between the central maximum and the first minimum, which we just did, or we're just talking about. Now, let's see what the equation looks like. Well, here you can probably best understand the equation. So the equation goes like this. It's a very simple one to use, and it says sine theta is equal to lambda over b. Okay, so sine theta is lambda over b. What this means is that if you want to find out what that angle is of dispersion, of diffraction, then you need to know the wavelength of the light that you're shining and the size of the gap, B, right? Because we saw here before that B was the width of the gap. So that's nice and easy. And for example, in a question they give us here, for an example, it says there are microwaves with a wavelength of 3 centimeters passing through a gap of 5 centimeters. What is the angle of the first minimum? So what is theta for the first minimum? Okay, well, this theta is already that particular minimum, and then you go up from that by doing new lambdas. So for the first lambda over b, the first minimum, it's really easy. You say, well, sine theta is equal to lambda over b, which is 3 times 10 to the minus 2, because it's in centimeters. Hopefully that's intuitive. And b is 5 centimeters, so that's 5 times 10 to the minus 2 also. And we end up with 0.60 for sine theta. So then theta is the inverse sine of that, and we have sine to the minus 1 of 0.60, which comes out to be 37 degrees, right? So 37 degrees is the angle at which this will happen. If you measured here the angle from here to the first minimum, that angle, that's 37 degrees. Similarly here, that angle there would be 37 degrees. Just spreading out. And on a graph where you very often plot on the graphs the angle, here you plot the angle and there the intensity, so that would be also measuring 37 degrees to the first minimum. That's what we just calculated now. Now notice that in the equation it doesn't matter if here you use meters and there you use meters, or here you use millimeters and there you use millimeters, because the ratio is going to be the same, right? I'm going to have times 10 to the minus 2 times 10 to the minus 2 top and bottom, so I could have just said, well, 3 centimeters over 5. Just make sure you use the same units for both lambda and for b, so that you can get the right answer for the angle of diffraction there. Right, so hopefully that makes sense for everything we've done here. It was a bit jumbled when I explained this here, but hopefully the other classes we've had explaining this made sense. And yeah, with this one, when you want to have halves, the easiest way to do it is like this. I think I gave you a different trick last time, but the easiest way to make sure that you have halves is, well, here n lambda, where n is for constructive interference, n is 0, 1, 2, 3, just a normal counter. And for this one, if you just use n plus a half, then you can also use the same one, 0, 1, 2, etc. Because that means that 0 plus a half, you will have 1/2 lambda. That will be your first destructive, which makes sense for this one. Then for 1 will be 1.5 lambda, which will be your second destructive range. Okay, for the yeah, so those are the general conditions for phase difference and path difference for destructive or constructive interference. Okay, well, this one is always measured in meters and this one is always measured in radians. Don't forget the radians. It's in 2 pi's for 360 and so on and so forth. It's not in degrees, so this is in radians. Okay, so I'll send you this to you guys to have a look at, and hopefully it will make sense. One thing I was going to forget to mention was, if you look at the formula that we just looked at, we just learned, okay, it's very easy to apply. It's a very ugly circle. Then notice that you know, sine theta has a maximum value of 1 always. If you plot the graph of sine theta, it looks like this. It goes to a maximum of 1, minimum minus 1, like that. So the maximum that this whole thing can be is 1. So when does that happen? Well, when this divided by that is 1, right? So this divided by that is 1, or closest to 1, when these two numbers are very similar, right? So when that number and that number are very similar, then the result of the division is going to be nearly 1. So that makes sense now that we were saying before that when the size of the gap is of the similar size as the wavelength of the light, that's when you get a maximum diffraction. So this angle would be the biggest, right? Yeah, in terms of from going from 0 to 90, okay? Because this is 90 degrees and the sine, that's 90, that's 180, That's 360, that's after one full revolution. So after 90, between here and here, the maximum can be closest to 90, right? You're not going to get a dispersion angle bigger than 90, because that would mean, you know, that would mean that the light's coming in like this, and then the moment it comes through the gap, it goes like somehow backwards. The most it can be is 90, and it's never that much. It's normally something around there. Okay, so then you're looking at this angle here. All right, so hopefully that makes sense. I just wanted to make that point. Yeah, that's it. All right, see you in the next video.